Okay. Oh, yeah, right. I got to get this fixed. Whoa. There we go. Hello, how are you? Welcome to Math 219. Oh, and I need to fix my audio settings here. Oh, it looks like I'm good. Okay, all right. Okay. Good morning. How are you? I assume everybody can hear me, just checking on the audio. Okay, good. Thanks. Welcome all. Looks like we have another minute and a half before class officially starts. This is a 10:15 start, I believe. Yeah. Right, right. Welcome everybody, or just arriving. Good to have you here. Almost time to get started. I'm going to go ahead and start on time. Okay, according to my clock, it's 10:15. We'll go ahead and get started. Welcome all. Thanks for coming. Weird circumstance, of course, that we're in, having to start the semester remote. for COVID reasons, which, good luck to us all. Optimistic about getting back into the classroom in a couple of weeks, whenever that is. Okay. I teach by way of screen sharing. So I'm going to just go ahead and share my screen now and start getting into it. Let's see here. Here we go. So I think everyone should be able to see my screen now. And I'm going to have to adjust a couple of things real quick. If y'all bear with me just a second, that needs to go over there. And I could put that there. Okay. Okay. So I am on the wrong screen here. There we go. Okay. So I've got some introductory comments prepared, just kind of about the basic functioning of the course, how this class is going to work. So let's go ahead and get that done first. Well, I guess the first thing I should say, if you're thinking about a math major, perhaps come talk to me at some point. Don't forget, I'm going to have office hours right after class, as my usual schedule. So that'd be a good time to come talk to me, and I'll show you in a minute how to get to those office hours. Okay, so the two Sakai sites are the first things that I should talk about after that. First, the course Sakai site. This is the Sakai site shared by all sections of the course, and it has information that applies to all sections of the course. There is, of course, a separate Sakai site for my sections. That is section-specific policies, information that applies only to my sections. So I try to keep things separated between those two. There's a lot of stuff there. We're going to click through a little bit of it right here, start a class on the first day, but we're not going to have time to do all of it. So I want to emphasize, you need to do this yourself. You need to read through all of that important information. There's a lot of information there. It is all really important to how the course works, policies, procedures, stuff like that. Okay. And by the way, you go ahead and click around on all the links. There's various links in there. You don't have to read all of the information on all of the links. Eventually, it becomes the internet, right? But at least see what I'm linking to in those Sakai sites. Okay. So think of this as your homework assignment for the first day of class is to do all that reading and exploring. Okay, so let's get into course operations. The first thing I'm going to do, I'm just going to jump right over to the syllabus, to the Sakai site here. Let me get over to it. Hang on, I'm almost there. Any second now. Sakai is slow. Okay, so this is the course Sakai site right here. You should all have access to that. Let me make this a little more legible. And the first thing I want to point to, I guess I should go to the syllabus first. Lots of information here. Notice in particular a list of all the instructors and all of the office hours for all of those instructors. Notice you are invited to the office hours of all of the instructors, not just mine, right? All of the instructors. My office hours are right after this class, pretty much. And of course, not in Physics 123. This is my office in the physics building. Temporarily, it's all Zoom. And there's a Zoom meeting section of the Sakai site. So you come right down over here to where it says Zoom meetings, and you tap there. And there you go. There's the links. Okay, it'll look different on your page, of course. Okay, a bunch of other information on the syllabus. Y'all are going to read through all this stuff. We don't have time to go through all of that. The content syllabus, or I like to call the content syllabus, is in some sense everything that we're going to cover in this course. So you'll see it has the book listed right there. And in that book, these are the sections that we're going to cover over here. Then you'll notice furthermore, for each section, or for most of the sections at this point, there are exercises listed. Those are the exercises that will be assigned for the homework. Okay, when they get assigned, we'll get to that in just a second. Okay, do notice that these are all colored in orange. All of these cells over here currently colored in orange. Orange means that that list is not yet finalized. This is my first time teaching the course, and I'm going to be going through and adding some homework exercises to some section, possibly removing some. We'll see. But obviously, currently there are 0 exercises listed for section 1.5. That's not going to stay that way. So stuff will be added. Once things are finalized, these cells will turn green. So keep that in mind. I hope to have the list for chapter 1 all finalized in the next few days. That'll be well before it's due. Okay. Let me stop share for just a second. And I just want to check and see what's so we've got 25 people here. Great. Welcome all. Let me also note that y'all are welcome to ask questions if you like. Feel free. If you do have a question, please just start talking. This is what I found over a year's worth of Zoom teaching last year is the most effective way. They have their little electronic hand raise and the chat, things like that. I honestly, I don't see it. All of these sort of electronic things, I just don't see them, especially when I have my screen shared, right? Just unmute yourself and start talking if you have a question, and don't hesitate to interrupt me. Please do not hesitate. I don't leave a lot of natural pauses while I'm teaching. So you just have to start, you have to interrupt me. It's going to feel weird first time you do it. It's going to feel like you're, rude or something, but it's not. That's how I want to do it in this class. So just interrupt me, please. That said, I will stop periodically to leave a little bit of pause in case anyone has a question. Okay. All right, back to sharing the screen. Okay, so going back to the list, let's see, we talked about the content syllabus. Let's move on now to the lecture schedule. That now is on, where am I? Here I go. The other Sakai site. So by the way, again, keep in mind, you're going to click through. There's a bunch of stuff on this course Sakai site, the policies on exams and homework. There's a bunch of important things here. You got to make sure to read all that. Course grades, etc. How I'm going to come back to that. Okay. So let's go over for the moment, though, to the lecture schedule on my course. On my section, Sakai site. So here it is, the lecture schedule. You see it's one of these sections on this Sakai site. And this has everything you need to know about the what and the when. So in particular, you can see today and our target, what I'm in theory, come on, highlight. The plan, fingers crossed, is that we will get through my introduction and section 1.1 and section 1.2. That's a target. It's a goal. It's wishful thinking, right? Aspirational. What actually happens, I'm going to record in these cells down here. And that, of course, I can't do until after the fact. Okay. The sections that we finish, so for example, presumably, hopefully we'll finish at least section 1.1 today. I will then document, officially recognizing that we have finished them, I will document those sections over here. So for example, I expect to put at least 1.1 into this cell over here on the right. Okay. Once a section has been put into this cell over here on the right, or any of these cells over here on the right, that's your cue that we have, because we have finished that section, you are now encouraged to start working on those homework exercises. I think it's a great idea to start working on homework as soon as we have finished covering the section in class. Okay, now when do you turn it in? You'll notice that the homework assignments are numbered here, 1, 2, 3, 4, 5, 6, 7, etc. And I've already kind of grouped together what days worth of material are going to be part of which homework set and when they're due. So you'll notice homework 1 here, it doesn't go by weeks. Every week is a little different, and it's just easier not to try to make a pattern. Homework 1 will include 4 lectures worth of material. So that homework 1, which will include all the exercises from the syllabus for these sections in this section here, will be due on Friday, January 14th. Okay, so I hope that pattern makes sense. Okay, all right, homework 2, things are different. There's a holiday. It's not the start of the semester. Everything's a little different. Happens to be only 2 sections, two lectures worth of material for that. A little bit different. Most of them are going to be 3. Typically 3 sections, but again, every week is a little different. Okay, the coloring, let me talk about that. These sections that are, these cells that are colored green, all the sections that are in those green cells are fair game for the green exam. All right, so exam 1 will cover all of that material. Now you'll notice then, for example, this cell right here is yellow. So that is not fair game for exam 1. I personally, all else being equal, I think it's highly suboptimal to have material covered on a Wednesday and then, okay, tests on Friday, right? I think it's better to give you all a little bit extra time to, digest. So when possible, I like to leave those gaps. So likewise, the yellow material, exam 2 is the yellow exam, comes a little after spring break, and then blue, etc. And then, of course, now everything is fair game for the final exam, and that's listed here as well. Okay, so I hope this all makes sense. Let me pause again for questions. Okay. All right. Back up to here, Zoom. So yeah, we're doing Zoom for the first, week and a half or so in this class. Yeah, it is what it is. Once we get back to in-person class meetings, I am still going to do the Zooms. I am just doing it though, just for the recordings. That's why I'm doing Zooms. It's for the recordings so that y'all will have access, if you're sick. If for whatever reason you can't make it to class, then I want those recordings to be there. So that said, I will notice attendance is part of your grade for this course. It's not a lot, it's a small amount, but a little bit. And Zoom participation does not count for attendance, right? This is an in-person course. Again, after these first week and a half. For most of the semester, this is going to be an in-person course, and attendance means in person. Okay. Now that said, if you're unable to make it to class, whether it's excused or not excused, you are also welcome to go ahead and join the Zoom if you like. That's fine, right? But it just doesn't count for attendance. So let's be clear about that. Okay, course grades. Now let's get back to the course grades thing. It is broad stroke. We're going to do grades on the 4-point scale. So 4 is an A, 3 is a B, like that. And it's going to be an average of various exams and homework and attendance, etc. Right? That averaging will happen on the 4-point scale. So on all of those items, you will get a number that's 3.72 or something like that. Okay. And each one of those exams is going to be curved individually. I'll show you where in just a minute. But the big picture, though, is that everything is going to be averaged on the 4-point scale, and it's a weighted average according to certain weights. Okay, off to the Sakai site where we have some details about this. Going back to the course site. Internet. Okay, there we go. Here's the, for all sections of the course, the weights will follow this rule. Every section of the course, the midterm exams will add up to 60%. How the instructor breaks those down is up to the instructor. And I'll show you my choice in just a second. Final exam will be 30%, again, for all instructors. And then there's 10% of kind of for instructors to kind of do whatever they want with. And when all those numbers get averaged, each student will have an average that falls into one of these bins. And so, for example, if you get, approximately a 4, then you'll get a course grade of A. Okay. And if you get approximately, a little above 3, but, closer to 3 than 4, right? Then that's a B+, etc. Okay. So these bins are mostly determined by which sort of standard 4-point number is closest, approximately, and there's little exceptions. Okay, so that's the big picture. More discussion down here. These are all things to be looked at when you're reading. Finer detail I'll give you on my section Sakai site. There's a course grades section. And specifically, here's how I break down that 60% for midterms. We're just going to make it even 20% for each one. Okay, and then the 10% that I have flexibility on, 7% goes to homework, 3% to attendance. Okay. All right. There's more details, such as exactly how homework and attendance scores are going to be computed. Y'all can read those details. I think it's very clear, and make sure to give a look to that. Let me show you the exam curves. After each exam, these numbers are going to get filled in. So after exam 1, I'm going to fill in, I'm going to fill in these numbers here. And pretty much the idea then is that's going to tell you exactly your grade on the 4-point scale. So for example, if you get a 79 on the first exam, let's say, perhaps, whatever's in this cell, it'll be like, I don't know, who knows, 3.6, let's say, 3.62, maybe, I have no idea, right? But perhaps this might say 3.62, and that means that the 3.62 is that's your actual grade on that exam. The 79 is just a sort of that's the score out of 100, but the meaningful grade, the one that counts toward the average, is the whatever number goes here. Okay. All right. So those curves will all be published right around the time of the exam, a little after the exam, something like that. Okay. Ditto the final exam, by the way. The final exam curve will be shared by all sections of the course. That will be completely fair. All sections will get treated exactly the same on the final exam. Okay. All right. Making good progress here. Pause before we go on. Any questions? Is everybody good? Okay. Okay, so the big point. The most important thing I'm going to say today, in terms of, what is our goal here? What is my goal for you? And that is for you to understand ideas. This is a course about ideas. It's not a course about answers. This is a big change for a lot of students, coming especially from high school math classes, where if you get the right answer, right answer is the right answer, and there's nothing else to talk about. And right answer means full credit, etc. That's just not what this is. What we're looking for is for you to give an explanation of the ideas and reasoning that goes into the solution of a problem. So you should think of every exercise, every exam question, everything that you do in this course, you should think of as this is, I need to explain my reasoning. It's almost like it's an essay question. And you explain the ideas that go into solving the problem. Okay, so very important fact. So we're interested in ideas. We're interested in reasoning, right? We are not so interested. Let me, by the way, move this over. This thing's in my way. Need to move. Sorry, I need to move that to like here. This is not a course about answers. It's not a course about whether you get the right conclusion. Okay, so for whatever it might be worth, I think it's convenient to point out this is actually how most university courses are, if you really think about it, right? I mean, what would happen if you go into a history class and you just memorize the book, you memorize all the names and the dates and the titles and the everything that happened, right? So and so was born on this date, died on that date, passed the such and such amendment on this date. Right? That's not what history is. History is about understanding. I mean, yeah, you have to know some names and dates, right? But it's about understanding how events relate to other events, right? And how ideas take over societies. And it's about big picture stuff, right? It's not about the names and the dates. And math is really no different in that sense. Okay. All righty. So keep this in mind. It's an important point. And you're going to notice that that's how I'll give my lectures, which I'm going to get to very soon. And you're also going to notice that that's the way exams will be graded, right? So the right answer at the bottom of the page with unintelligible work getting to it does not get credit. That's just not what we do here, right? So you have to explain your reasoning. Your workflow has to make it clear what your reasoning was. And in some cases, it's appropriate to document what your reasoning is, maybe with a couple of words. Doesn't have to be a lot, but just a little bit. Okay, we'll say more about that later. Okay, all right. So again, just to emphasize on exams, points are awarded on the basis of the validity of your reasoning, the completeness of your reasoning, clarity of thought, clarity of communication. Okay. All right. By the way, if you want to see some examples of the kind of things I'm looking for, you can look into the Sakai. There's a link on the Sakai site that goes to all of my old exams with all of my solutions that I've written. And I always write my solutions with an idea in mind of this is the example. This is an example of the kind of work that I would like to ideally get from a student in the course. Okay. All right. Okay, there's a bunch more stuff to say here. I don't have time to go through all these details. I'm going to point out that this file is in the Sakai site. Let me point to it. In my section Sakai site, you're going to go to the resources section and somewhere, okay, come on, internet. Gotta wait for the internet to catch up. There is a folder called lecture notes. Click on that page called lecture notes. And this file right here, first day notes, this is what we're looking at that I'm going through right now. You'll also find the intro file, which is sort of the intro to the material. And then my lecture notes, as such as they are at the moment for chapter 1, they're almost done, not quite. But anyway, that file there as well. So throughout the course, the way you're going to find my lecture notes is in this folder, this lecture notes folder in the resources section. And I'm going to, every time I write more lecture notes, I will periodically upload into this folder. What appears there is always the most up to date that I have at the moment. Okay, so please download this file, the others as well, of course, but this file that we're going through right now, and read through all of this stuff down here. This is all really important. I do want to say, though, real quick, though, the big picture point to a lot of this, certainly this first part here, is that we're not going to cover all of the material in class. There's not enough time. It's not even close. We just can't, right? So what I'm going to do, the way I give my lectures in this class, is I go through all the stuff that is in the book that you're responsible for, right? And I put together a lecture that I think is going to be most helpful for y'all in your process of learning that material. And it just won't cover all of it. Right. And I want to emphasize as well, I put together that lecture with the idea in mind that you're going to be doing a lot of your learning outside of class. You're going to be doing a lot of your learning using the lecture recordings. Right. So when I'm talking to you in class, I'm talking to two versions of you. I'm talking to you now, but I'm also talking to you later. I am expecting you later to be listening on the recording, and you later has had more time to digest and has had a chance to, read through the book and come to office hours and kick some ideas around, et cetera. And you later, has advantages over you now. So anyway, keep that in mind. It is not the expectation that you can just come to class, listen, and that's where you learn stuff. And then outside of class is where you do the homework. That's not the plan of the course at all, right? It is expected you'll do a lot of learning outside of class. Okay. Let me pause for questions. This would be an appropriate time for a pause. Okay. So I want to talk a little bit about now why is multivariable calculus important? Why are we here? Why do you have to take this class? Right? Or why have you chosen to take this class, perhaps? And it's I think it's an important question to address. Appropriate time being now, start of the class. And so let me remind you, already know why single variable calculus is important. Right? You've taken single variable calculus. You know a lot of single variable calculus. Derivatives and integrals, but specifically, why do we need to know derivatives? Well, because the world is full of stuff that changes. That's what derivatives are. In fact, one could argue derivatives are more broad than that. Derivatives show relationships between quantities, right? And if one of those quantities is time, then you're talking about how, rate of change. Right. But there's no law that says one of them has to be time. It might just be a relationship between two different quantities, and a derivative talks about that. So very, very important thing. Integrals. Why are integrals important? It's because we compute how things accumulate. That's the way I like to say it. So you think about integrals as area under a curve, perhaps. You'd be surprised how rare it is that we actually need to know the area under a curve. That the primary, fundamental reason we need to compute an integral is because ultimately we need the area under the curve. That's really actually pretty rare. Most of the time that we compute integrals, it's because we need to compute some quantity, and that quantity can be computed by a Riemann sum, which is an integral. And the area under a curve is a visual aid in that process, I suppose, but it's not ultimately what we really need. So anyway, derivatives and integrals, we want to understand how things change and how things accumulate, which is, of course, huge. So here's the thing. The world is three-dimensional. World is not one-dimensional. And so these questions become really, really different in, the 3D world that we live in, right? I mean, it's a different thing. So in particular, maybe I'm looking at, position in space. I got X, Y, and Z defining where I am in space. And then I'm moving at some angle. Also, that's described by a vector. Of course, direction is described by a vector. A vector has 3 coordinates. So I've got a bunch of different parameters, right? I'm in a certain place and I'm moving in a certain direction. And then I want to know, as I do that, how is temperature changing? Right? Well, this isn't a single variable calculus problem. It's about how stuff changes, but it's about how stuff changes in the real world and not, on the x-axis. Right? So the world's three-dimensional. It makes calculus problems harder. That's what we're here to understand. Okay. Likewise, maybe I'm trying to keep track of mass, and I've got a mass where the density is not constant, and maybe the density depends on 3 different variables. It might depend on where you are, described by 3 different coordinates. How do you compute that mass? Well, sometimes you get lucky. If it should happen to be that even though it's a 3-dimensional thing, but the density only depends on 1 variable, then you can make clever single variable calculus arguments. But if the density depends on several variables, single variable calculus doesn't cut it, right? And if you want to know the mass of something, if you want to know how much of this accumulating quantity called mass actually accumulates over this actual solid, That's a much harder problem. That is not a single variable integral, and it's a multivariable integral. So these are two of the kinds of problems. This is just a tip of the iceberg, I emphasize, right? But these are two of the kind of problems that we're going to study in relation to the three-dimensional world. Let me pause again for questions. Okay. I emphasize, I mean, please feel free. If anybody has a question, don't hesitate. And again, don't hesitate to interrupt me. Again, that's the process. You got to interrupt me. Okay. Okay. Applications. I'm just going to throw some applications out there, just for kind of the visceral experience of seeing, oh my gosh, this is where it actually, why do I need to know, kind of thing. So here's the kind of thing that economists do. And that, by the way, I made up this equation. This isn't a real equation, but this is representative of the kind of approach that very often is taken in economics. Namely, you got a bunch of different variables. And if you've taken an econ class, you might recognize, price, quantity, interest rate, capital, labor, right? I mean, so people in econ talk about that kind of stuff all the time. And you build an economic model, and an economic model is usually not this one's a function of the others. It's usually, well, these things relate in a certain way. There's some equation that involves all of them, but it's just an equation. And you might not be able to solve for the one that you're actually interested in. So for example, if I want to know the rate of change of P, right? Well, here it is. Can I solve for P? Well, tragically, no, not even close. Just can't do it. Algebraically, just can't do it. And yet it remains that I want to know how P changes. In particular, I want to know how P changes. If I have control over how these things are changing, I want to know how P is going to change. Right. So how do you do that? Well, what we have here is another kind of a multivariable calculus problem. And this is something that we'll talk about in this course. Now, the big thing I want to point out about this one, not only is it that, how econ is done is with multivariable calculus, a little bit of an overstatement, but nevertheless. Furthermore, notice that there's more than 3 variables here, right? We have 5 variables right there that you can see. And I like to say 5 plus 1 because that expression there, that's an important quantity, right? That thing, I don't know, maybe I call it W or something, right? That's something I need to study in the process of understanding the green variables. There's really 6 variables involved here. And a lot of people make a mistake when they're thinking about multivariable calculus, and they think, oh, look, the world's 3-dimensional, so you shouldn't need anything beyond 3 variables. That's nonsense. Absolute nonsense. We study more than just position in space in various applications, econ being arguably one of the least scary of the fields that uses multivariable calculus, right? You can see very easily here that understanding calculus of more than 3 variables is routine, right? This is an abstract sort of like rare, manufactured type circumstance. This is routine everyday situation in a very, very applied field of study, namely economics. Okay. All right. Okay, now real quick, I'm going to wave my hands at some more physicsy, some more sort of expected areas where multivariable calculus is needed. Here's Maxwell's laws, or a version of Maxwell's laws. If you need to study electricity and magnetism, these are the rules. And you may have seen these in a physics class. If you haven't, don't worry about it, no problem. But if you have, again, might look familiar, and reasonable questions come up. What does this all mean? right? For one thing. And it turns out that most of what's written down here on this page is multivariable calculus. We're going to make sense out of all these objects. And then also, it turns out that a lot of these statements are actually related to each other. So this equation right here and this equation right here, now they look very, very different as equations. It turns out that these two statements, if you understand multivariable calculus, actually say almost exactly the same thing. Very, very similar. So how could these two very different statements, my gosh, this one doesn't even have an integral in it, right? This has got loads of integrals, right? No integrals in this statement. And I claim that they say almost exactly the same thing. How could that be? Well, there are some important ideas of multivariable calculus that are going to allow us to make this connection and see why it is, in what meaningful sense is it that these two equations actually say the same thing. Okay. Chemistry, physics, Schrödinger equation, right? So now this is quantum mechanics and it's sophisticated, but this is ultimately, if you want to know how electrons form molecular bonds, kind of a big deal in chemistry, right? The way that we describe the rules that electrons follow that result in molecular bonds is, well, it's Schrödinger's equation, and it's this, and this is actually a bunch of multivariable calculus. Now, we're not going to study Schrödinger's equation specifically, but we are going to study the tools that go into understanding it. Okay. All right. So, and then of course, there's lots and lots of more applications. These are just a couple of quickies. So what I like to say, and I already kind of said this, but multivariable calculus is the calculus of the real world, right? Single variable calculus happens on a line. Multivariable calculus happens everywhere. Okay, pausing again. So that's my intro. Any other pauses? Any other questions? Okay. Again, feel free, chime right in, unmute yourself, start talking. I hope I'm not missing people. I hope people aren't screaming at me and I'm not hearing it. I don't think so. I had some audio success with students at the start of the recording, but anyway. Okay. Moving on now into the actual material. Chapter 1. Right, the Kali textbook, which, by the way, I have the textbook here also, and let the record show I like this textbook quite well. I like this textbook a lot more than the textbook for Math 212 that was used for many years. So I'm really happy that we're using this book. There are a few things about it that maybe aren't quite perfectly to my preference, but that's the way things go. There's no such thing as a perfect textbook. Okay. So we're going to go really fast through chapter 1. And the reason why is it's a lot about linear algebra. This is Math 219. All of y'all have taken Math 218, and 218 is linear algebra. So you should have seen all this stuff before. So I'm going to pick and choose very, what's the word? Flexibly in going through chapter 1. Most of it is stuff you've seen before. Now, I emphasize it still would be a good idea for you to read through and make sure that you feel comfortable with all the stuff in the book in these sections that we're going through as we do them. Make sure that you're up to speed and polished on this material that I will be assuming that you are good with. Okay, so there's very little that I'm going to say about section 1.1. I think y'all have seen all of that. I just like to point out the book uses bold to indicate a vector, and I think that's kind of a flex in a way, because they can do it, and we working with a pencil can't, right? So I mean, I guess technically you can, instead of writing V, you could sit there and, kind of do like that. But, realistically, who's going to do that, right? Realistically, it's much more convenient to do something such as putting this little arrow over your vectors. So that little vector hat, much easier to do. That's how I prefer to write it, and that's how I would like it to be in the book if I had my choice. But again, minor quibble. Okay, so heads up, you're going to notice in my notes vectors will look different. Another little quibble, and this is not a big deal, but this vector here representing an arrow going from P1 to P2, the book writes that as P1, P2. And okay, sure, that's fine. That communicates that it starts at P1 and ends at P2. But of course, we can also write that as P2 minus P1. Keep in mind a very important fact about the way we think about vectors and the way we think about points is points really are themselves vectors, right? So thinking of these as vectors, that arrow, what have I got here? This green arrow here, right, is P2 minus P1. So I prefer to write it as P2 minus P1 for the very simple reason that it shows algebra, right? And algebra is useful. And I would rather see the algebra. I mean, you can always, of course, say, well, if I need it, I know that hidden inside of this notation, there is algebra that I could write down, but I want to see it. And it's not like it's all that much harder to actually do so. So anyway, you're going to notice me writing things like this, and you're probably never going to see me writing anything like that. Okay, it's
Is there a reason that there's a hat over P2 but not P1?
It was pure oversight on my part, and thank you for asking. So yeah, I'll get that fixed as soon as I think about it. But yes, there should have been a hat there. Oh, and I guess, come to think of it, I guess maybe the book puts a vector hat over there. I'm not sure. I'll have to look and see what they do there. But thank you for pointing that out. It was oversight on my part. Okay, how are we doing? Is everybody on board? Okay, I'm going to leave that there as a reminder to me. Okay, so section, that was 1.1. We're already done with the section. 1.2, we're probably not going to finish today looking at the clock. We have until 11:05. Yeah, so we probably won't finish today. But I want to get started with 1.2. It is a bunch of stuff about vectors. And so again, most of that y'all have seen before. Make sure you read through, make sure that you are fully polished on all the stuff that I'm not going to talk about here. But I don't suspect y'all have probably seen parameterizations. So I do want to talk about parameterizations for a little while here. Parameterization is a way of describing a curve, for example. We'll talk about parameterizations of surfaces later. But a parameterization of a curve just gives position as a function of usually t, which you think of as time. So think of it as giving position as a function of time. So for example, you might say, well, look, my x coordinate is going to follow this rule and my y coordinate is going to follow this rule. And if you know where you are as a function of time, then you can think of that as that the parameterization actually draws the curve, what we call a parametric curve. So this is a parameterization. For example, position as a function of time. This draws a curve. This tells you where your pencil should be at any given point in time. And then again, that traces out the curve. Now, what does this draw? If you don't recognize this one, which you might well not, have never seen parameterizations before, let me point out that this formula for x and this formula for y, those formulas, cosine and sine, well, they satisfy this rule. So that means that every point that comes out of this parameterization because it satisfies that equation there, that means that every point that comes out of this parameterization is on that circle. And that kind of gives away the game. And you can persuade yourself that as time goes along, what's actually happening here is this is tracing out a circle. Does everybody see what happened in that example? It's a sort of an easy starter example, but is everybody on board? Okay. All right, now here's a harder example. This one you kind of can't really eyeball exactly, but here's a parameterization. Do keep in mind when you see a parameterization, that first formula, that first coordinate formula is your formula for X. And that second formula is the formula for Y. And if there's a third, then that's Z. Okay, so what is this one? What is this, this formula? What is this parameterization? Well, there's a couple different ways that you can come about this. One thing you can do is you can infer what T is from one of them and then stick that into the other one. I missed. Stick that into the other one like that. So if T is X plus 1, then 3T plus 4 is, well, there you go. And 3T plus 4 is this, which is this, and now you've got an equation relating X and Y, and this is recognizably a line. So that's one way to do it. Now there's a different game that you can play to get that same result. I don't know, pros and cons. I like to kind of start with one of them and then ask, does this look like the other one? I see a T minus 1, and does that look like 3T plus 4 kind of in any, you know, broad strokes? I mean, you know, does it look kind of the same in a way? And then play with it and get it to turn into that other thing. So notice if I just multiply by 3, now you got to be fair, got to do that on both sides. If you multiply by 3 and then add 7 to both sides, notice that we've kind of turned that into that, namely Y. And having followed along, of course, with what you're doing to X at the same time, that then gives us the same relationship between X and Y. So suit yourself. Different circumstances, one of these might be easier than the other. How we doing? Okay. Moving along. And this last one, you kind of have to, this is a harder one. This is in 3 dimensions. And neither of the above really quite works here. There is not a single equation that these all satisfy that gives away what it is. You can't, it just doesn't really quite work. What you can do, though, is think about the X and Y coordinates. They describe the projection to the XY plane, and it's really clear that that's a circle. We already know that that's a circle. But then we can also realize that the Z coordinate by itself, right? Well, that's just, Z is just T. It's just kind of going straight up. So the point that we're looking for, this point that's, you know, sort of moving along, well, its projection down to the x-axis is on the that blue circle. It's that, you know, kind of moving around like this, and its, you know, projection over here to the z-axis is going up straight, you know, at a constant rate. And so all together, you just kind of combine them together in your mind. You've got this is what the XY shadow is doing. And then you've got that is what the Z shadow is doing. And then you try to do that at the same time. It's, you know, it takes a little coordination, right? But kind of like that. And you can kind of persuade yourself that it's making this helix. Kind of like that. Everybody with me? Okay. There is no sort of single, it'd be nice if there was a little mathematical hopper that I could toss a question into and out would come the answer. It's always by hook or by crook when you're trying to understand parametric curves. They're all different, and different tricks that can be useful for different kinds. So these are 3 tricks that I think are useful. And so, you kind of have to combine those in various different ways. So I tell you what, I think this is a pretty good place to draw the line. This is how far we got today. We did finish with section 1.1. We did not finish with 1.2. And I'll note that on the lecture schedule, and we will pick up here on Friday. Welcome to Math 219. I look forward to working with you. Don't forget, I have office hours in about 10 minutes. Which I showed you. Yeah. So course Sakai site, click on the Zoom meetings section, and then you click on my office hours. See you later.
Thank
and
you.
I'll stick around.
Thank you.
Yeah, pleasure.
Thank you.
Thank you.
Nice to meet you.
I just have one quick question. Where could I find the book on, do we have to buy the book or is it on the page?
I can't post or in any way share the PDF file of the book. That would be a copyright violation by Duke University, and we just can't do that. That said, I was able to find that PDF, and you may be able to find it as well. But that's pure speculation, and I have no comment on how to do that or anything like that. Physical copy of the book, of course, if you wanted it, you'd have to buy it. One way or the other, you do need to have a copy of the book, because that is where the exercises will be pulled from, most of them anyway. Those are your options.
Awesome. Thank you very much.
Good thing.